Here is the plan for today. We will use a Sawyer robot as an example. Try to convince you guys how vision could improve this kind of task, like how to guide the robot motions. Later, Amazon picking challenge, and of course, state-of-the-art deep learning for motion. And the second part will introduce you some like robot models and also the Move It package. So in lecture 3, we talk about AppleText, and you could actually see AppleText in this demo. And we also, in lecture 5, we talk about the transformation matrix. So for the Sawyer robot, that's a 7 degree of freedom robot arm. And I guess by now you guys are able to like do this pulse composition, and then to get the location of the gripper, right? Later, we will cover the robot model. And essentially, there is the file is called URDF. Inside the URDF, you could define your own robot. For example, you could define some of the links. For example, basic link. Essentially, that's one entity there. And wheels 1, 2, 3, 4. There are 4 wheels over here. And then you could also define each one over here. You could also define the joint. For example, here there is a base to wheel 1 joint, maybe somewhere around here. And also some other joint called arm 1 to arm based, maybe here. Okay. And yeah, you could define the type could be fixed, or it could be revolute. The interesting part is that you could also define some limitation there so that the rotation can be limited within some angles. Did we mention anything about Move It package before? Yeah, it's slightly different from AMCL or other like G mapping. And essentially, Move It is a package that with a framework for motion planning, manipulation, 3D perception, kinematics, control, and navigation. That seems a lot, but essentially there are some established motion planning algorithm already integrated pretty well in this Move It package. It's quite popular. In 2015, there are 16 papers in total cite Move It in IROS and ICRA conference. Okay, and today we will also cover this in our tutorial with the RV's motion planning plugin. Okay, so we will just try to play with it and see how it works. And it supports more than 60 robots, including, for example, the Husky robot with UR5. It also supports Baxter, supports Sawyer, or other robots. Okay, so that's the good thing about Move It. How to improve it? It's not perfect so far. For example, there are something people would wish to have in Move It. For example, sometimes the planner will generate suboptimal paths. Okay, maybe the algorithm is not that good, so that the planning result is not satisfactory here. And the second thing, I think also about planner, so it sometimes generates a plan that's too close to an obstacle. For example, last week we talked about Voronoi algorithm. You have 1, 2, 3 obstacles, and what's the Voronoi algorithm do? And you wish that your path is stay away from them as much as possible, right? So for those 2 obstacles, you can draw a line here. So every position on the line, it will be away from those 2 obstacles, right? Another line and the other line there. And the other important one to be improved would be that currently when the planner plan a trajectory, there is no easy way to replan it. so that you could assume that your environment is a static environment. Yeah, nothing really changed if you want to plan this trajectory. Okay, but in reality, it's not always true. So that currently the MOVE-IT did not integrate with the visual or the tactile feedback very well. MOVE-IT has been also used widely in Amazon Picking Challenge 2015. In fact, there are more than 10 teams use MOVE-IT, Amazon Picking Challenge. You could think that if you are doing this competition from 0 to 1, if you have nothing and I want to form a team from scratch, maybe MOVE-IT is a good tool to get started because it already gives you some fundamental functionality. But in 2015, none of the winning teams used MOVE-IT. So for the number one team in 2015, RBO, it used some kind of sensor-based transition. It actually relied on vision a lot, and also with a simple but robust object recognition algorithm. And for Team MIT, it used another planning library called DRAG. And DRAG was previously used for the DARPA Robotic Challenge. If we move on 2016, and this is the winning team, so let's take a look of this one. Actually, this one used MOVE-IT. Yeah. There is a great development environment set up by Gazebo. We covered this in the class. They use a faster RCNN, and they train it with 20K images, and the other 500 label image is each class. And we cover those topics in vision and deep learning in our class. And they use an algorithm called Super for PCS and try to match point cloud to CAD model. And we cover some of the 3D perception in the class. And also they use the RRT algorithm. They also use MOVE-IT. They also use inverse kinematics. I would like to also introduce you guys the state of the art, how people use enforcement learning for motion. This work is done by the BVLC group. We have also mentioned this. And we also use the CAFE tools from this group also. So let's take a look. Now we should have a...
We present a method for end-to-end training of deep visuomotor policies that map camera images and robot configuration directly to motor torques. Our convolutional neural network policy has 7 layers and 92,000 parameters. We vary the position of the target in each task, perform insertions with only a millimeter of tolerance, use a variety of different grasps that must be determined from images, and screw bottle caps onto bottles. Here, the policy must determine the distance to the rack from binocular images to successfully place the hanger. The policy generalizes to racks with clothes, without additional training, as well as small objects on the hanger such as towels. Here, the robot inserts a block into a shape-sorting cube. The policy was trained with the cube in the robot's arm, but generalizes to the cube sitting on a table. The hammer task is performed with various grasps, which the robot must identify by watching the toy hammer and its own gripper. The policy generalizes to placing the hammer under the nail in the presence of clutter. The bottle task requires screwing the cap onto the bottle. This visuomotor policy also generalizes to the presence of clutter in various positions. The The policies use input from a monocular camera to complete the task. Camera images, together with the robot's configuration, are processed at 20 Hz to produce motor torques. For the hammer task, the policy must infer both the position of the target and the current grasp, while the bottle task requires precisely localizing the bottle opening and rotating the wrist to tighten the cap. Here we show a variety of visual generalization experiments. The insets show the camera images that are fed to the policy. The hanger policy can handle different hangers and large objects that cover part of the view. The insertion task succeeds in the presence of new objects in the background, and can even insert the block when the cube is held in a person's hand. The hammer task can also be done with an arm in the seat, as can the bottle task. Here, the robot follows a moving target. The target did not move during training. When we cover the monocular camera, the robot is unable to localize the target or determine its grasp. The policy attempts to reach an average target position. When the scene is revealed again, the policy makes a last-ditch attempt to recover. This indicates that the camera images are actively used by the policy. The trained policy can fail when we change the mass of the hanger and cover large parts of the target object, or when the background changes dramatically, altering the brightness of key features such as corners. Here, the gray shirt appears similar to the robot's gray arm. And here, the policy attempts to recover from perturbations, which put it in states that are too different from training.
I think this is a wonderful work. And then you could see that the only input is the vision, right? And then there is no calibration needed. And the other video shows the features. Yeah, so this semester we also cover lots of the features and what the feature looks like in the deep learning, in the convolution neural network. So let's also take a look at the features.
Here we show visualizations of the policy's representation of the input images. For successful insertion, the policy must localize the shape sorting cube. The policy finds a few feature points on the bottom left corner of the cube. It also finds feature points on the top left corner and on the right gripper. For the hammer task, the policy must localize the toy bench and determine the grasp of the hammer. The policy robustly finds a few feature points on the bottom right corner of the toy workbench and a feature point on the bottom left corner. The policy also finds points on the robot's gripper, relevant for determining the grasp of the hammer.
This is a summary of this course. I hope that this course help you to be well prepared for your research. And we cover low and high level detection and recognitions. We cover the features and deep learning. We cover 3D perceptions. And we also, of course, sense, plan, and act. Your robot can do some cool things. I would like to thank all of you for contributing the in-class tutorials. Okay, and I hope to work with you again soon, hopefully in sensing and intelligent system next semester. And maybe some of you, if you are interested in joining the ICT co-working space, that would be wonderful. And hopefully NCTU will form a team to compete Amazon Picking Challenge or other competitions in the future. I hope you guys, everyone has downloaded the VirtualBox. So now I will just give you guys a brief introduction of this tutorial, what you are supposed to see when you do this. I have installed those packages for you inside the VirtualBox image. And you could see some of the package here you may be familiar. So when you see anything about description, that's more or less about the URDF files or the XACRO files to define your robot. We also have MoveIt installed here. Okay, and this part to compile the code, I think this book, Learning Rust for Robotics Programming, second edition, I think this one it's pretty good. It covers many of the topics So we will just git clone this code, put it in a Rust book folder. We try to compile it. And one thing I would like to mention is that in the chapter 5, it actually used a non-free package in OpenCV. And that's only available in OpenCV 2.4.9. So over here, we just simply put the kkin ignore inside this folder. And then you could just run kkin make and compile the code. And this part is done already. And when you try to run the code, you could just call Rust launch robot 1 description and try to show the robots in RVs. So maybe you could just do this. So I would just copy this and then try to put this. Okay, maybe I should go back to the kkin workspace. Yeah, I need to source the setup.bash in order to get those packages and then try to run it again. Okay, and now we also need a config file for RVs. So we could just go here and try to open the config file over here and open it. So you will see the arm over here. You could try to zoom in and rotate it a little bit and move it around. And the good thing is that there is an interface for join state publisher. And over here for the ARM, we actually have 5 of them. One is from base to ARM base. So if we move it around, can you see the ARM is rotating? Okay, and here is the second joint if we move it around. And you could definitely play with this inside your own VirtualBox image. And next, ARM 2 to ARM 1. Okay, and here we also have 2 joints, the left gripper and the right gripper. Let me try to zoom in, try to rotate so that you can see the gripper better. So it's over here. And let's try to open the gripper. All the models definition, you could see it in the URDF file, okay? And that is inside. If you are in the dev kkin workspace, and that's cd into source chapter Rust book, I guess, and then chapter 7, and it's everything. All the model definition will be in the something description. Description here, and we could take a look at the URDF, and we can bin into robot 1.urdf. You could see the link, so let's just slash link. Okay, so you can see a link, a basic link over here, and you could, this is a basic link, and you could also see the wheels. And we have wheel 1, and if we move down, wheel 2, 3, and 4. Okay, we have 4 wheels over here. Okay, and we definitely need 4 joints to attach the wheels on the basic link. Okay, base to wheel 1, 2, 3, and 4. I will just quickly go over this definition. And there are something else, some other definition about inertial, about the weight, etc. But let's just take a look at the joints for now. So you could see the joints base to arm. And some of them we already play with it in RVs, try to adjust the joint state so that you could move the arm somehow. Okay, so you could see base to arm, and also arm 1 to arm base. So I hope you could play with this within your VirtualBox. You can also try to randomize those values, and you will see the robot arm try to malfunction somehow here. So this will be the part 1 talking about the robot model. This is another interesting example here. You could define a robot model in XACRO, And in this format, you could include some plugins, some modules, so that you could reuse some of the parts. So let me just try to run it. So I hope that you will see the same thing inside your VirtualBox. So you will see the same one, essentially the Universal Robotics, the company, they provide the ROS package. So if you install ROS Indigo UR-start, you will pretty much install everything, including the description and some other stuff. So now let's try to set up the environment variable here. So I will just try to put the command inside. And you could follow the detail of the Husky UR5 tutorial here. It's over here, but you could actually skip the installation part. Okay, and now I will just try to put have 3 terminals. Okay, so this is the first terminal. It tried to open the same Husky environment and also open the Gazebo environment. But the only difference here is that now the Husky has a UR5 arm on board. Yeah, you can take a look here. So this is the Husky robot with a UR5 on top. So let's open the second terminal and then try to run the Husky UR5 planning. Okay, and lastly, let's open the RVs with the Move It plugin. Okay, so now we can see the interface here. At the bottom left, this is the Move It plugin inside RVs. And you could actually try to play around with it. And today I will just show a very basic scenario that let's try to move the robot arm, the endpoint, to a certain point. And then the planning, you could use the planning, which is included in the package about the inverse kinematics. Okay, and you could also try a different planner and see how it works. So essentially, let's try to click this point. And you could see that now we have an orange part of the UR5. You can see it move around here. Now I will hit this button, plan. Okay, and it's planning now. Oh, it's failed. Sometimes it may reject where you placed. So maybe let's move it to maybe something maybe a little bit simpler here. Let's do that again. So here is the plan. And so far, if we go back to Gazebo, so the robot arm is not doing anything. Now let's try to hit execute and let's see what happened in the Gazebo. Okay, execute. Okay. Okay. So here is when you hit execute, the robot arm will follow the trajectory and move it to the point you designed.